Okay, this week's review topic is going to be universal law of gravitation. You can read at the top of the page that the universal law of gravitation shows us how to calculate the gravitational force between two objects from their masses and the distance that separates them. The law includes a value called the gravitational constant, or G. This value is the same everywhere in the universe. Calculating the force between small objects like grapefruits or huge objects like planets, moons, and stars is possible using this law. We see a model drawn here of a mass, probably the moon, that is a distance from the Earth. You'll notice that the distance separating them is measured between the object's center of gravity. We've seen this equation before, that the universal law of gravitation finds this big F. We would mark that big F, big G, because we're going to use this gravitational constant, big G. We're also interested in the mass of both objects and then the distance separating those two objects. We call that R. The gravitational constant is this teeny tiny little number, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. That negative tells us that it's really small. Some of you might have that particular portion of the value dropped out just to make the calculations a little bit easier. So when we have two masses, like we have here, M1 and M2, and they are given in kilograms, remember that's the unit for mass, and the distance that separates them is in meters. It's the unit for distance. The force has the unit of newtons. Remember that 1 newton equals 1 kilogram meter per second squared. So anytime we're calculating with gravitational force or any other force, we like to work with units of kilogram and meters and seconds. All right, so the distance separating them is R, so that this value right here is R, okay? And so it looks like here we have two masses that each have 1 kilogram of mass, and they're separated by their radius, and each of them, looks like they're uniform, is 0.3 meters. So the total distance separating them is going to be 0.3 meters plus 0.3 meters, which will be 0.6 meters. So if we plug all of this information into the equation, we have big G here, M1 and M2, and then there you see the sum of those two. This is the radius, and that gets squared. Don't forget to square the radius. All right. There's a little note at the bottom of the page that says a small car has a mass of approximately 1,000 kilograms. So here we're looking at approximately the mass of a car. Trying to visualize this much mass compressed into a sphere with a diameter of only 0.3 meters. It's pretty tiny. If two such spheres were touching one another, the gravitational force between them would still only be 0.000185 newtons. On Earth, this corresponds to the weight of a mass that's equal to only 18.9 milligrams. The gravitational force is not very strong. So on the back of the page, I'm going to work through two of the problems for you. I encourage you to stop and replay the video as much as you need so that you can make sense of the work I'm about to show you. Looking at number 1, you're going to calculate the force between two objects that have the mass of 70 kilograms and 2,000 kilograms and are separated by a distance of 1 meter. So we're given mass 1 is 70 kilograms, mass 2 is 2,000 kilograms, and the distance R separating them is 1 meter. We're asked to find force. I've already given you the equation that you're going to use. You'll notice the only other thing that you'll need to finish the calculation is big G, which is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So now we just plug everything in and we calculate. F is equal to G m1 m2 r squared. So we plug that in, we're going to get 6.67 times 10 to the negative 11th Newton meter squared kilogram squared times 70 kilograms times 2,000 kilograms, all divided by 1 meter squared. Now don't forget the order of operations says that we need to multiply these two things first, and of course dividing by 1 really doesn't do anything to our value. It doesn't change it at all. So when we continue multiplying here, we're going to get 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. We're going to take 70 times 2,000. 7 times 2 is 14. And if I add the 4 zeros after that, I'm going to get 140,000 kilograms squared over 1 meter squared. Remember that when we square, the 1 meter, it's 1 times 1 is going to be 1. And if I look at this now, my units, meters squared, cancel with meters squared, kilogram squared, will cancel with kilogram squared, and I'm going to end up with the correct units of newtons. So go ahead and take your calculator. Ignore this for right this second. Just do 6.67 times 140,000 and see what you get. All right, checking your work, you should have gotten 933,800, and then I'm just going to tack on the times 10 to the negative 11th newtons here. We're going to ignore scientific notation for right now and just leave our units, our values in these rough form. Okay, I'm going to go on to number 2 now. So we're asked to calculate the force again between 2 touching grapefruits. So right now the objects are touching each other. They each have a radius of 0.06 or 8. So I get for writing on top of it 8 meters. So I'm going to double that and I'll get 0.16 meters for the distance separating them. And both of their masses are going to be 0.45 kilograms. Okay, so now when we plug these values in to the equation, we have 6.67 times 10 to the negative 11th, and then we've got 0.45 kilograms times 0.45 kilograms. Assuming we're working with 2 identical grapefruits. And then I already doubled their radius, so I know that the distance separating them is 0.16 meters squared. Don't forget to square the 0.16 before you do anything else. So I'm going to give you a moment so that you can simplify 0.45 times 0.45 and 0.16 squared. So we will fill in the top and bottom here in just a moment. Okay, here we are again. So 0.45 and 0.45 will give you 0.2025. That's kilograms squared. 0.16 squared, that's 0.16 times 0.16 is 0.0256, and that's meters squared. I forgot to write my units over here, but they will help me keep track that the meters squared cancels and the kilogram squared cancel. Now we're going to take 6.67 times 10 to the negative 11th newtons, and I went ahead and did this calculation already, and that's going to be about 7.91. So now we need to do 6.67 times 7.91. Go ahead and use your calculator to do that calculation. All right, you should have gotten 52.76, and remember that we're multiplying by this times 10 to the negative 11th, which means it's really not a big amount of force at all. It's really tiny because of that negative exponent. So I'm going to ask you to go ahead and try number 3, 4, and 5, and remember that I'll be on office hours on Tuesday between 1:30 and 2:30 if you want to work through some of these problems with me. See you then. Bye.